In this video, we shall discuss the evaluation of double integrals. So let us consider this example. Evaluate integral 1 to 4, integral 3 to 5, x square y dy dx. So here we note that the limits are constants. The region of integration is a rectangular region as the limits are constants. So it is as shown in the figure. Y varying from 3 to 5 means it is a line parallel to x-axis, that is y equal to 3 and y equal to 5, and x equal to 1 to 4 means they are the lines parallel to the y-axis, x equal to 1, x equal to 4. It is as shown in the figure. So this is x equal to x equal to 4, and this is a line parallel to y-axis, x equal to 1. This is y equal to 3 and y equal to 5. So the region bounded between these lines is the region of integration. So now let us evaluate this integral. Integral 1 to 4, integral 3 to 5, x square y dy dx is equal to integral 1 to 4. Since the order of integration is we integrate first with respect to y between the limits y equal to 3 and y equal to 5, and then with respect to x between the limits x equal to 1 and x equal to 4. So x square is considered as a constant, hence we keep it outside the integral and we integrate y dy. So we get integral 1 to 4 x square, integral of y dy is y square by 2, evaluated between y equal to 3 and y equal to 5. So now when you substitute the upper limit, it is 5 square 25 minus 3 square, that is 9. So 16 by 2 is 8, and hence we get integral 1 to 4 8x square dx. Now integrate x square dx. So we'll get x cube by 3 evaluated between x equal to 1 and 4. That is 8 into 4 cube is 64 minus 1 cube is 1 divided by 3, which gives 21, and the resultant is 168. So this is an example for evaluation of a double integral with constant limits. Now let us move on to how to evaluate an integral with variable limits. So evaluate integral 0 to 1, integral x to root x, x y dy dx. Here we note that the limits are not constants. We can observe that the limits are variable limits, y varying from x to root x varying from 0 to 1. So this shows that the region of integration is not a rectangular region, but it is a region bounded by the curves y equal to x, y equal to root x equal to 0 and x equal to 1. So the region of integration is as shown in the figure. So here y varies from x to root x, that is y equal to x is a straight line passing through the origin. This is the line y equal to x, and this is the curve y equal to root x, which is a parabola, and x equal to 0 is the y axis, x equal to 1 is the line parallel to y axis. So now we shall integrate this function xy with respect to y and dx, y and x. So now since we are integrating first with respect to y, x is kept constant, hence it is kept outside the integral. Integral 0 to 1 x into integral x to root x y dy dx. So integral y dy is y square by 2. Hence we get integral 0 to 1 x into y square by 2 evaluated between y equal to x and root x dx. And that gives half into integral 0 to 1 this x into substituting the upper limit, that is root x whole square, we get x, minus substituting the lower integral, so lower limit x, we get x square. And on simplification we get half into integral 0 to 1 x square minus x cube dx. So that is half into integral of x square dx is x cube by 3 minus x cube is x power 4 by 4. Evaluated between 0 and 1, that gives 1 by 24. So this is an example of how to evaluate a double integral with variable limits.